Oh, hello. The ships that you've been seeing for the last few minutes are a good example of the recreation that people often find around the water. And this recreation is a direct result of buoyancy. Buoyancy is what makes these ships float, and it's what makes fun occur on an open body of water like this river. These ships are less dense than the water, and they float. There's also many other parts of buoyancy though, and in this video we like to explore any misconceptions about buoyancy and clear up any ideas that
Hi, let's talk about the concept of buoyancy. Buoyancy is the relationship between the density of an object and the density of the medium in which the object is located. The Greek scientist Archimedes discovered in 212 BC that an object immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. There are three cases. Case number one. If the density of the object is greater than that of the fluid, the buoyant force will be less than the weight of the object, and the object will sink. If the density of the object is equal to the density of the fluid, the buoyant force and weight of the object will be equal. The object will neither sink nor float. Case number three. If the density of the object is less than that of the fluid, the object will submerge only until it displaces a volume of fluid with a weight equal to the weight of the object. Let's try it out. Let's demonstrate case number one. I think I have a quarter here. Oh yes, I do. This quarter is denser than this water. Let's see what happens. The quarter has sunk to the bottom of the sink. Let's demonstrate case number two. This case is when the object neither sinks nor floats. Here's an example of case number three. As you can see, the object is floating.
Hello again. We've already stated that certain objects float, while others sink in the same medium. This, of course, has to do with density. Also, we stated that Archimedes' principle says that the weight of fluid displaced by an object in a medium equals the buoyant force on that object. Let's talk about this a little more. When we threw the quarter into the sink, it sunk. Why is that? The reason is that the amount of fluid that this quarter displaces is very small, perhaps less than a milliliter, which means that the weight is only about a gram of fluid. However, this coin weighs more than a gram, so it sinks. On the other hand, this boat displaces a few milliliters of fluid, maybe 50 milliliters of fluid, and therefore that's about 50 grams, which is a lot more than what this boat weighs. So therefore, the boat stays on top of the water.
We've already established that this boat will float on water. Now let's see what happens when we try to place it to the bottom of the sink. Boat goes down. Boat goes up. Boat goes down. Boat goes up. One more time. Boat goes down. Boat goes up.
Okay. We've already established that the boat will float on top of the water without sinking. This is because the density of the boat is less than that of the medium in which it's floating in. But why is it that when we put the boat on the bottom of the sink, it floats immediately to the top? Let me explain. The water pressure at the bottom of the sink is higher than the water pressure at the top of the sink. Therefore, the pressure at the bottom of the boat is greater than the pressure at the top of the boat. Now, everyone knows that boats move from high pressure areas to low pressure areas. So, the boat wants to move from the high pressure area at the bottom of the sink to the low pressure area at the top of the sink. Therefore, it goes up. Special treat. We're going to act out the way in which Archimedes discovered some of his famous principles. As the king was sitting on his throne, he was struck by a violent thought.
Gee, I wonder if this crown is actually made of pure gold. I know. I'll ask Archimedes.
Oh no, I'm sinking!
Archimedes! Archimedes!
Oh, hello, King.
Hi. Archimedes, would you please find out if this crown is actually made of pure gold?
This crown?
Yes, that crown.
That'll be very difficult, because to make sure it's pure gold, I'd have to find the exact density. And to know density, you have to know not only weight, but also volume. As you can see, this crown is irregularly shaped, so finding the volume would be very difficult. But I'll think about it.
I know you can do it, Archimedes. Ha, 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 ha.
How will I ever find the volume of this hat? It's too irregularly shaped. I just don't know how I can find the volume. Maybe I'll put my hand in this water. Oh, wait a second. When I put my hand in the water level rises. I bet if I put the crown into the water level will rise. Then, by measuring the change in water level, I'll know the volume of the hat. Let me try it. Oh, King.
Come in, sponge bath boy. I've been waiting.
No, King. It's me, Archimedes.
Oh, come in, come in.
I've brought your crown, and I'm happy to report that I've discovered its true nature.
Thank you, Archimedes. I am forever in your debt. Come, have a sponge bath. Let's take a look at Archimedes' principle in action. Given the volume of a cubic decimeter of steel, given the density of steel, and given the density of water, you can find the magnitude of the buoyant force and the net weight on the body. Here are the equations. Here are the equations in action.
Is essentially the same as buoyancy in water. Objects that are less dense than air tend to float, like these balloons. The reason why these balloons float is because the total weight of the helium in them and the rubber that surrounds the helium is less than that than the air in which the balloons displace. So, therefore, they float in the air. Also, the air pressure, once again, at the top of the balloon is less than that at the bottom of the balloon. So, moving from high to low pressure, the balloons have a tendency to float upward. Hey, you're not taping this, are you?
No, no.
So that's buoyancy in a nutshell. And next time you see something floating, just remember, buoyancy.
slop.